funding for it, and then he was able to change things and pull it through. So now it's a big success, and one of the things that we're going to look back on, like landing on the moon, is an extremely important tool in our understanding of the world, understanding of the origins of the universe, who we are, why we're here, who else might be out in our world, and really trying to bring an understanding of science to everyone in the world, really. And I think the importance of science is becoming clearer and clearer as we're seeing people embracing non-scientific theories of all kinds of conspiracies and things like that. So I think we have to understand how important these advances are in terms of giving everybody in the world a great grounding in what science is and how it could contribute to our lives. So Thomas, I'm going to turn things over to you. We're going to run through the program, and then if people have questions, please post them in the chat, and I will try to feed these to Thomas as we wrap up. So Thomas, take it away, or take us away.
Yeah, thanks. Just want to confirm that you can hear me okay, Rob?
Everything's great, yes.
All right, so look, I'm really excited to be with you virtually here in Ann Arbor. And thanks for everybody who's calling in, including one person from Bern, Switzerland. I saw somebody send me a text, and I have to figure out how to direct message back, but I'll figure that out later. What I wanna do is talk to you about one of the most magnificent, the most complex, the most expensive telescope that is currently roughly 1 million miles away from Earth, and is getting ready to start operation in a month or two, focused on looking at towards the edge of the universe, the first galaxies, the first stars in the universe. So what I'd like to do is just next slide, tell you a little bit about what the ideas are behind Webb. Why would you want to study infrared light? It's going to be a theme. Infrared light, of course, the radiation of warmth, so to say, right? Kind of, it's very much kind of a heat signatures from deep space. So it's not light that's invisible with our eyes, and so we're going to talk about that, because that's what Webb is all about, and then kind of what are the things we're going to see, and then focus on some of the stories I thought I'll tell you about the telescope, perhaps a little bit behind the scenes. Yes, this is both a magnificent opportunity, but also has been a magnificent challenge. Challenge we've really struggled with over time, and part of that we'll talk about also. So the next slide is focused on the next chapter. I want to say is focused on Webb. How did Webb come to be? And the next slide, of course, shows you kind of the lineage of Webb. So overall, there was a kind of infrared mission called Spitzer that we stopped operating in 2020, just before COVID started. It had run out of its coolant, and frankly, it has been a modestly kind of resolution telescope. Was our first opening, kind of, if you want, into that space. Chandra, which is an X-ray telescope, is still up there. It's looking at that violent universe. Remember the release just of the black hole, the image of the black hole, kind of with it came in that press release, kind of the environment of that black hole lighting up in X-rays, just like the doctor uses, or even higher energy in the sky, lighting up the environment. That's what Chandra would image. That is still up there. And then, of course, the Hubble Space Telescope with its story focused on visible light and ultraviolet. You see, kind of, if you go across this, you see a whole gamut of kind of low energy, which is infrared, to mid energy, which is Hubble, and then high energy. Hubble, in many ways, is the most successful mission we've ever done thus far. It's 31 years or so into operation. Of course, it too had amazing stories. First of all, its money overran. And then when it launched, you remember, it was out of focus. And it was out of focus, it turned out, not because of the way I always think about it. It's not because of E equals mc squared, not because of complicated physics, complicated optics, complicated this, because of something simple. namely a technician, not believing their test and basically making a part, to basically continue the test instead of saying, hey, something was done wrong with this mirror. And so it's the theme you're going to hear kind of later in the stories is all about this. Hubble, the most iconic image of Hubble is this one. You got it, Megan. Is this one, which is the ultra deep field image. And kind of just think about this. Think about looking through a soda straw into the sky. That's roughly how much sky you're looking at. It's the darkest part of the sky we could find, which is somewhere near the pole, kind of near that Big Dipper. And what you see is thousands and thousands of galaxies, all kind of stacking up into the deep universe. This, by the way, was kind of collected for 11 days. What you see is a three-dimensional animation that's using the Doppler shifts of certain lines to kind of guess how deep the galaxy is in the universe. And so you see that basically in that soda straw, there's between 5,000 to 6,000 galaxies. So if you looked at all soda straws, you go all directions into the sky, and every direction looks roughly that way, you'd have 100 million galaxies, each one of them hundreds of millions, has 100 millions of stars. So kind of the universe is way richer than you would have possibly guessed if you looked at it with your own eyes. And the reason we know that is because of that amazing data that was released in 2015. So just absolutely incredible. The next basically image, of course, shows you some of the specifics of that. And you could really talk about each one of them having a story. The Crab Nebula, for example, is an exploding star 1,000 years before Christ, and then basically, there are, for some of these stars that are actually, documents, sometimes in the Chinese culture, sometimes in the European cultures for later ones that talk about stars that are exploding, supernovas, then the Crab Nebula, again, in X-rays and so forth is expanding. The Ring Nebula, in many ways, is a dying star that has shed its atmosphere, and there's almost comet and dust-like particles all in the outskirts of it, creating that ring. Each one of them has a story. The universe is incredibly, incredibly beautiful. So basically, the question is, once you look at these nearby, what I told you with Hubble looked like a really deep sky. Well, it's not that deep, actually. We can go a lot deeper, but you need to look at infrared to go there, because, of course, as the universe is expanding, the farther back you go in time, the more red the light turns. Just because the universe, it's almost like if you have an explosion, whatever is the farthest away flew away the fastest. You know what I mean? That's one analogy. It's not the correct way to think about it entirely, but it's a good way of saying if you look farther, the speed is faster by which it goes, and therefore it's more red. As the light is shifted more red, just like the ambulance going by, the Doppler effect, the sound changing, the light is also changing. All right, the next slide is basically now telling you, right? Okay, so I already mentioned before, there's a whole spectrum we could look at, and really what we're trying to do is move towards kind of being on the right side of this visible light, where our eyes hang out, and kind of the magnificent pictures that I just showed you mostly occur into an area which the last time we looked at it, we did so with very low resolution and not nearly as far into the infrared as we want to go. And frankly, that's what we're trying to do. Kind of one way of thinking about it is that the whole universe, we believe, based on everything we know, is 13.8 billion years old. So, kind of if you looked at the man my age and basically say, hey, the equivalent is 13.8 billion. So what we're really trying to see is the baby pictures of the universe, kind of going all the way into the childhood, if you want, of the universe. And basically our hope is that we get to something like 100 million years of the Big Bang. So kind of that very early youth of this, kind of with the first galaxies that are there. And everything I've shown you with Hubble is much more today's galaxies, which is already utterly magnificent. So it's just imagine what happens if you take away that kind of that cover off the camera lens, so to say, that we've never seen. We've never seen the universe that way. All right, next. So if you do that, if you want to go back in time that much, there's fundamentally two things you have to do. And this is a first design, which, by the way, didn't work. Kind of whenever you do something new, the first thing almost never works. It's just matter of fact. I cannot remember one where we got it right at the beginning. But what you have to do is really two things. You have to make a telescope that's really cold. In fact, the back of the telescope, the instrument, the coldest instrument that goes the farthest into IR is 6 Kelvin. Remember, 0 Kelvin is that absolute 0 point in nature where kind of the nature stops jiggling because of temperature, right? It's kind of that, it's that absolute 0 point that well beyond minus 250 Celsius, and God knows how many Fahrenheit. Sorry, somebody knows that number, Rob. Spurt it out if you know what 0 is. I don't know it by heart, but so we go at 6 Kelvin all the way there. So it needs to be cold. But when you also look far, you've done it, right? You stand on a mountain, you want a telescope that has good resolution. So it needs to be big. So that the mirror needs to be big and it needs to be really cold. So that's what we're trying to accommodate. It turns out those two things are really hard to do, which is why Webb is a very complex telescope in many ways, because the moment you want to make the mirrors big and we want to shoot it into space, it still needs to fit into a rocket. Well, if it doesn't fit into the rocket with the full expanded mirror, you need to fold the mirrors. So you have to invent a whole new set of technologies you never did before. And so basically big and cold is really where it's at. So the early designs, of course, starting kind of frankly, the ideas about this in the late 80s, early 90s, and then the first technologies to really start developing these technologies. Kind of think of it like 10 to 12 entirely new technologies nobody had. The sensors that are flying, they were not in existence before that. So we had to invent them. How to fold a mirror and focus a mirror, we didn't know, we had to invent it. So basically there's a dozen technologies like that. And that's really what the point is of that slide. The next slide is again focused on infrared. I just want to kind of dig a little bit deeper. Why would I care about infrared? I'm going to go pretty quickly here because that's what I want to do. Overall, just a couple pictures from the Los Angeles Zoo, and you see kind of two animals. One of them meerkats. And of course, meerkats are warm-blooded animals that are small. And so basically, when you're small, your surface to volume ratio is higher. And so therefore, the meerkats need to produce a lot of energy to keep their bodies warm, which is when you look at infrared, you immediately see they glow like in the night, right? In infrared because of the heat that they're emitting. Take a crocodile on the other side, which is a cold-blooded animal. And, even though there's, of course, it has some energy to let this organism going, it's not nearly at the level that it's there. You can actually read off the temperature off the right, doing just like you measure the fever. We all became specialists in that in the last 2 years, how to measure your temperature with radiation, which is of course we can do with every star, with every galaxy. So just for you to kind of make that connection, the next slide is then focused on kind of the specifics of where we want to hang out, kind of at that kind of infrared range. And you see Spitzer it was kind of is kind of we're bracketing kind of Hubble and Spitzer, but go kind of in terms of the imaging. Spitzer was nowhere near there. And in fact, there's some pictures that are making the news right now. There's some amateurs put together. It's stunning where it's overlapping, but that's where we're going. Microwaves, by the way, are also important, that they're not what we're doing here. But, you know, if you want the Nobel Prize for understanding the microwave background, you know, was all about the concept of that initial beginning of the universe. We refer to sloppily as the Big Bang, which of course is imprinted into the sky in all directions at radiation, at some 2.5 or so degrees temperature variability. And then basically we learn a lot about the universe from ground-based observations and some space-based in microwave, but where the stars are at are in that infrared range that James Webb Space Telescope does. Next slide. Tells you kind of how you look at stars, kind of in various areas, you know, and this, of course, you know, is you know, one of the most, you know, one of the most important pictures of Hubble, kind of the pillars of creation. We talk about that, which of course shows dust cloud, invisible. You see, it's mostly dust. Immediately, your eye immediately picks up, oh, this is like a dust, kind of a dirty kind of fog and dust that is there, and then that's exactly what it is. These Eagle Nebula, the pillar of creation, kind of really in the visible light, shows that when you go to the mid-infrared line, you basically can peer through that. With some places it's too thick, right? So you cannot light cannot make it through, but you can see through it, and you see some of these new stars that are forming in there. And frankly, when you go to the mid-infrared, you can go beyond, actually see behind these pillars, kind of really, and look at the glow of the heat that comes from that dust as the stars are heating up, the dust and the gases that are around it. Kind of my point is, each one of these wavelengths tells a story, and you can peer through kind of foreground to look at the background in much more accuracy and much more, you know, with much more focus than with visible alone. So the next slide then is really about Webb, and so go next. So let's just quickly look at the time. I already talked about the Big Bang at the beginning and what happens after the Big Bang, and kind of think of it as this enormous explosion that's imprinted into the sky in microwave kind of sounds, kind of the echoes of that, which in all directions are observable from the ground, to the surprise of these two you know, electrical engineers that looked at the sky with their World War II antennas and found this noise. You know, it's like, what is it? Somebody say, wait, I predicted that this is what should happen at the beginning of a universe, which of course was in Einstein's theories of relativity, that even though Einstein himself did not believe that it was a scientifically valid solution. He called that in German his biggest is a lie, his biggest idiocy, kind of that he did not believe his own equations as much as he should. So that happens, right? And so what it's very much energetic. Basically, the gases start forming. At the beginning, there's no atoms, right? The atoms start forming, and as the universe expands, they cool down. And then all of a sudden, kind of the atoms start aggregating around each other, creating big kind of clumps of matter, and stars start igniting, reionizing, kind of charging back up the environment. So it's hot, cooler, and then hot again, because it gets hot again because of the stars lighting up. And so basically, we think these stars assemble into galaxies. There's stuff that is not on that chart that's also important. And I want to remind you again of the black hole that was in the news in many newspapers about the fold this last week. Black holes and galaxies go together, and we're actually not sure. And we want to figure out whether black holes are already happening early on, kind of early on in the universe, or whether they be a consequence of galaxies forming. So that I cannot make that chart, right? It's there's a third element that just to mess with your head. So of course, so I'm showing the stars that are bringing together. I just told you black holes also matter. There's a third element, and that is that roughly 85% of all matter is not visible. We call it dark matter. We know that dark matter also is part of gravity. And kind of every galaxy, look at our own galaxy, any other galaxies, 85% of the mass is dark matter. Where dark matter is in this, whether dark matter is a really important part forming that together with the black holes and the mass, we don't know. So those are the kind of pieces of the puzzle that play, kind of that need to be understood today if you want to understand galaxies. What we want to go back is to see the first generation galaxies, kind of the to really observe that and make sure we understand the science of galaxies in general, of our universe. Needless to say, the galaxies are creating the environment for stars like ours to have planets that form life. So for us, that's where our thinking is. All right, so enough astrophysics. So to get a thought, you can ask, what's the oldest galaxies we've ever seen? You see that fuzzy thing? It's kind of at the very edge of bubble, you know, with a lot of error bars, kind of probably older than 13 billion years. It's the oldest galaxy we've ever seen. That's the record so far. Again, focused on you know, trying to push back in time. Again, Hubble really was not made for that particular observation, just because it was not red enough. It's not cold enough. It's in low Earth orbit. So it actually gets heated up by the Earth too. So it just, but that's the best you could do at that moment in time. So that's what we're trying to beat. Next. And yeah, so basically, then the question is, if you build, like, you know, I always think of this like a picture book of a kid. You may have children, right? And if you go back in time, see the baby pictures, and then all the way to the teenage or grown-up pictures. So basically, the question really is, over time, what are the galaxies? How are they evolving? And what are each one of these factors? The black holes, the dark matter, the physics of the gravity, the accumulation of matter, how do they really form to these magnificent objects in the sky, which frankly take your breath away when you see them. We, of course, being part of one of them, if you're in a dark sky, see that light band over the sky doing that. All right, next. So when we built this, frankly, that was the only point we were focused on. But what happened in 1995, some of you may remember, the first stars were announced outside of the solar system. First planets were announced outside of the solar system. Exoplanets, we call them. They're all exoplanet with one exception, where we have a candidate elsewhere, we just announced last year, are observed in our own galaxy. And what actually happens, molecules, you know, like you take O2, like they're like two oxygen, they can oscillate like so, back and forth. That is also in the infrared. We know that on Earth. And so basically by looking at molecules and star-forming regions and in atmospheres, we can do more science. The next slide shows you some of these kind of infrared light kind of things. This is the best we can do right now to try to image, kind of to find other planets. You see how kind of messy it is around there. What we're trying to do is block out the light of the star so we can see the planets going around. You see them slowly moving around. This is the kind of image we're trying to do. And with Webb, we'll have enormous opportunities to, of course, get better than that. Next. So basically, you know, the atmosphere, you know, our own atmospheres, but also atmospheres, they have imprints of the composition of the atmosphere. Now, the one thing you have to remember is our atmosphere is shaped by life on Earth. You breathe, what you breathe is CO2 out of your mouth. Nitrogen in our atmosphere largely, we believe, comes from life on Earth. So kind of the atmospheres are shaped by life on Earth. And so the question really is, next slide, what are we able to see in atmospheres of other stars? So with that in mind, So basically I just want to point to the fact that, this is the kind of stuff. I just want to give you some pictures for you to get a sense. So first of all, this telescope fully expanded with these mirrors is 21 feet across, 6.5 meters, if that's what you do. And again, needs to be folded up. You see there at the bottom right, because it does not otherwise fit into the rocket. So each one of those pieces, the 18 pieces, need to be aligned individually to make one big mirror that is there. The next slide. It kind of gives you the comparison between Hubble and Webb, and it's everything that you need to see is evident from this chart. By the way, 2.4 meters is what Hubble is. Next. And again, each one of the mirrors is not the most important thing. It's the instruments that are there, both as imagers and also spectrographs. So spectrographs, are instruments that split the light, like into its colors, so we can actually decode where it is and look at spectrum of the type that I just showed you in the atmosphere. The next slide tells you where it is. I already told you it's a million miles from Earth, and it's the opposite side of the sun. So if you wanted to find it in the sky at midnight, look into the sky where the sun was at noon before, the day before. So that's where the telescope is. A million miles, that's roughly 1% the distance of the sun and the Earth. It's a Lagrangian point L2. You can put something there. It's where gravity and centrifugal forces are balancing each other. And that's where it is. That's where it has been. And I'm going to just show you how it got there next. By the way, it's deployed. Frankly, go next. I'm going to show a movie of that next. So again, I'll show you some of this. So in the optical portion of Webb was put together, already I had shown you, and then it was pulled. Sorry, you're going a little bit faster than I can speak. So yeah, so the optical portion of Webb was pulled together, and then next slide was assembled for the last few years in Rotunda Beach, and then you see at the very end of that, you see that big container that is pulled by a truck. That's where the telescope fit in. They could not fit into a plane. There's no plane big enough, so needed to ship it to the equator, the northern part of South America, to French Guiana. We wanted to ship that. That's when they're arriving. When it's arriving in French Guiana, you see the European flags back there. It's the European spaceport. The next slide showed you how it got there, which is, of course, with that ship that was there. We were all following it, and we had all kind of nightmares of trying to get famous with a single bullet, shot bullet against the container. That thankfully did not happen. We arrived there. By the way, it was secret, the details of where it was, for that reason, for security reasons. Next. So there we were, late December, and frankly, we had tremendous challenges with this telescope. I told Rob earlier, and I'm telling you now, that when I joined my job 6 years ago, I noticed, my mentor, Len Fisk, had told me, focus on the easy things. Like, that's where the mistakes will happen. I noticed that we had made a number of mistakes, so many mistakes that basically we were close to standing still for almost 2 years. So every 6 months we made a mistake that took 6 months. Now, I hate to break it to you, but as a taxpayer, I'm a taxpayer too. Each day of working on the ground costs roughly $1 million. And so basically 2 years of standing on the ground, immediately, these mistakes were killing us. And frankly, it put real doubt into our mind whether we could do it. We had to replace a lot of the leaders, to really get the whole team aligned. Many of the right people were there. They did everything they could in their right mind, but the culture was not. So finally we're there. You see the rocket in the back, and there's the three of us. The CEO of the company is on the left, I'm in the middle, and the guy in charge of the European Space Agency's launch program. We made that picture and told each other, those are the three positions that become free if something goes wrong with that launch, because it's $10 billion sitting on top of a rocket. You don't survive that if something goes really badly. So we were really becoming close as friends, working and trusting each other, and really making that French team our own friends, frankly, which is the reason that this launched on the 25th. I want to tell you, this is the first and only time so far that the French company Arianespace worked on Christmas Day. When I thanked everybody after launch, and not one, not two, but multiple told me that they did as a favor to the American colleagues, so they too could go home and celebrate Christmas, although delayed by a day, with their families. That's why they launched on Christmas Day. So I think that's the best indication of team. You do something that may kind of be not in your best interest, but to help others to make a better team, and that's what they did. So there we were the next day. Next slide. The rocket took off into the sky in the morning of the 25th. Some of you may have seen it on TV. We had an enormous amount of people spending their Christmas mornings with us as we were there, seeing the rocket disappear. And of course, the problem is usually when the rocket is up, 80% of the risk is retired. It's really risky to launch, and 20% is the rest. Here it's the reverse, because what needs to happen is what's shown next. By the way, before I show, this is the final picture of Webb, camera that we put on top of the rocket. You see the telescope moving away, the adapter ring that was attached to the rocket kind of looking at you, and it's moving away from the Earth. You see the Earth down there as it went to that million-mile journey to its final destination at that Lagrangian point. So I love that picture. It will be forever one of my favorite pictures, because it showed that we got through launch okay, and everything is still in one piece and so forth. Stuff we worried about during years. Next. So what had to happen now is, of course, setting up the telescope. And so what you see is 4, 5 sun shields that are the size of a tennis court at the bottom of it, that needed to, of course, protect the telescope from solar radiation. These sun shields had to be deployed entirely autonomously, 344 things, actuators, everything had to work exactly right for this, and then the deployment of the mirrors to work. That is the largest such number of single point failures in every mission, any mission ever done in space. 3 times harder than landing on Mars in terms of its accuracy and so forth. And so the telescope, it deployed, frankly, without any huge challenges. There's the secondary mirror coming out, and then that mirror's being deployed. I sat there when the final mirror got deployed with the team, and we all celebrated, because we knew that what was achieved was an enormous feat of humanity, kind of getting a beast like that into space and deploying it with enormous challenges. The next slide shows you where we are now. By the way, that's the URL in case it didn't work. The next slide shows you where we are now. Each one of the instruments working, everything is in focus, and we're now calibrating the instruments. And I have to tell you, kind of late June, early July, you're in for a treat, because for the first time, you will see how the universe looks, the baby images of the universe. Nobody has ever seen that, and this telescope is going to show it to us. We're extremely excited, the entire team and tens of thousands of people. We already have the first year of observations all planned out, and we can't wait to get started. And that's really where we are right now. Rob, next slide and final slide. Thank you so much.
Unbelievable. That is an absolutely most fantastic presentation I've ever seen. I'm still trying to get my head around all that you have had to pull out to get this to work, Thomas. So I'd like to ask people to post questions in the chat, and we'll go from there. Let me just ask you, Thomas, in terms of what was your most anxious moments during this?
Yeah, of course, standing next to the rocket, right? I had practiced the evening before both speeches, including the negative speech, right? I had both speeches in my bag. the one that I was going to give if everything went badly, because that was up to me to do that speech right there. So I was anxious. But I have to tell you, it was not what made this hard. It was not a moment. It was 2 to 3 weeks of anxiety, because every day we were deploying another piece. And, you know, I went into the lab, you know, the ops room before, and then I only went back at the end. And the simple reason for that, the way we always do it, we say, is test as you fly, fly as you test. So I was not there for all rehearsals. So I'm not going to be there when they're deploying. I couldn't be there for all rehearsals with my work. So I was really anxious, kind of waiting every few hours an update. Did everything work? Because, you know, any one negative update is basically the end of the whole dream, depending on what it is, right? So that's what. So it's a whole time of anxiety, not just a moment, Rob.
So we have a couple of questions. I'll just ask people to unmute if you want to ask your questions. So Bill Milliken, can you unmute and ask your question, Bill?
Yes, I wanted to know why we launched in British Guiana.
Yeah, that's a good question. I mean, frankly, when I came into the job, it was already done. There's that deal was made. It was one way for the Europeans to contribute. At that time, 20 years ago, we actually had a huge crisis of launch vehicles in the United States. We had none of the reliable launch vehicles we have today. So it was the most reliable launch vehicle at that moment in time that was there. French Guiana is where the European spaceport is. Because of the fact that it's by the equator, it takes less energy to get off the planet. So it also helped us by going to French Guiana to have kind of the heavier telescope accommodated. But I have to tell you, kind of, I had many dreams where I wished I could launch from the United States and just go to Florida, you know, instead of going to French Guiana with the mosquitoes and everything. But nonetheless, they were amazing guest Europeans, and but you know, these things are always a part of history, right? Kind of moment in time the decision is made. That is what it is. It saved the American taxpayer going there probably $500 million. That's the other thing you should see as a positive, but I'm not sure whether that. Anyway, that's the answer.
So another question from another scientist, Neil Weinberg. Neil deals with the thousands and thousands of systems that go into babies. He's a pediatrician in Ann Arbor. So Neil, what's your question?
Yeah, thanks. Really enjoyed the presentation. So we had a presentation a few months ago about the Mars landing, and it struck me, you know, I think there's something like 92 or 97 precise events that had to be absolutely perfect in order to land that rover. And you mentioned you got 344 potential single failure points. So I was interested in, how do you test each one of these points independently? And then how do you test them in sequence before launch?
Yeah, it's a really hard question. I mean, kind of, I could talk for this for a year, right? But basically what we're doing is every one of the single points, we do multiple tests independently. In some of the cases, we're also doing them in series. You know, when that mirror, you know, that heat shield came out, what had to happen is something like 50 of them had to fire in series. So first of all, we made each of them redundant. So if a circuit didn't work, there was a redundant circuit that had to fire. So we did all of them. And I want to tell you, something like 3 years ago, one of these redundant circuits did not work. And we tried to figure out why that is, because of the fact, you know, like, you know how this goes, right? If it's, you know, it's if the likelihood of failure is 1%, that to the 300s is almost certain failure, right? Kind of, so you have to knock down the error. We actually had to redesign that particular release mechanism. We redid that. Even it worked 250 or so times, but it didn't work in one case, right? It's like not fair enough. So we do that, right? Kind of both system, but also overall, we did the whole deployment of everything you saw in the lab twice. And basically end-to-end everything, kind of, to make sure that we could do that. In some cases, you know, where the telescope comes up, gravity, you cannot do that with gravity. So what you have to do is offload, create an apparatus that eliminates gravity, right? So it's kind of exactly, so it feels no gravity when it comes out. So it's the testing of this is an art in itself.
Thomas, I have a question. I'm just trying to grasp the enormity of the universe. Can you give me some help when you talk about hundreds of, what did you say, hundreds of millions, hundreds of billions of galaxies? How many were you saying?
Yeah.
Galaxies?
So let's do first the size and then the number. Are you okay with that?
Yeah.
So basically, if you look at the sun right now outside, no, don't look at the sun with your own eyes, but you get the point, right? So if you look at the sun, the light that arrived here left the sun between 8 and 9 minutes ago. Okay, so because the sun is that distance from the earth. Okay, the universe is 13.8 billion years old. So the light that's going to hit the telescope, if it's 150 million years after that beginning of the universe, has been in the universe at the speed of light coming your way for 13.6 billion years. So just, I hope that messes with your mind like it does with mine. That's how big the universe is, right? And if that's the visible universe that we're going to observe. Okay, now you can basically say, if I look at one galaxy, take our favorite galaxy with the Milky Way galaxy we're part of. In that galaxy, there's a couple hundred, about 400 billion, 400 billion kind of stars that are there. 400 billion stars. So in the universe,
yeah, go ahead. There's 400 billion stars in our Milky Way?
In our own Milky Way.
Wow.
So the universe has about 100 to 200 billion galaxies that we've observed, that we derived so far. And we may be slightly off, we may have to correct that. So now, one more thing you need to know, what we've learned in our own galaxy, for each star, there is at least a planet. We did not know that when I went to school. So just imagine all these potential livable worlds out there. Just think of it. Again, 400 billion stars in our Milky Way, 200 billion galaxies in the universe. So fair?
Is it fair to think of, you talked about an explosion, and an explosion goes in all directions. Is it fair to think of the Big Bang as the center of this? But is there a center of the universe? No,
I was kind of think of it more like the two-dimensional version is that we often use in class is kind of, you have a balloon and you make dots on it, blow air in it, and kind of everything, the dots are moving away from each other, right? They're expanding. You say, where is the center? Well, it's not on the balloon sphere, it's somewhere in the middle, right? Kind of the point is that the whole universe is expanding. From everybody's point, it looks like they're the center, right? So they're kind of, there's not, you kind of don't think of it like an explosion in space. Space is created as part of that explosion, right? So there is no space before. Space-time gets created as part of that explosion. Yeah, it's messy in your head. And if you gave me another hour or so, I could make it a lot more explainable. The most important thing to take away is you look at the stars, what you're looking at is much more magnificent and majestic than you would have ever guessed. It's just incredible what's up there, and we're part of it.
This is almost as complicated as psychology. So
not quite. No, astrophysics is a lot simpler.
Kabir has an interesting question for us. Kabir, you want to speak up? Kabir Meja, you out there? Well, let me read the question. Go ahead.
Okay, go ahead. I'm driving, so I didn't want to inject background noise. If you don't mind reading. Thank you, Thomas, for the amazing presentation.
Yeah. So your question is, should you look at Zoom while you're driving? The answer is no, Kabir, if that's the question. But the question he posed is, what new science is Webb going to enable? What specific gaps in our understanding of the universe is it going to fill?
Yeah, so again, what we're really going to focus on are a couple of them. So we're looking at the universe in an entirely new way. What we're really trying to do is look at the ancient universe at the ancient universe, kind of really the first galaxies that are there in infrared, you need the resolution. So that for us is what motivated Webb in the first place. What we're also going to do, and I think it's going to be probably more or equally important, if not more important, is really look at atmospheres of planets outside of our solar system and look for kind of signs of habitability of those atmospheres. So we're going to look at planets and learn more about their atmosphere than we've ever learned about any atmospheres other than the ones in our solar system. So for me, those are the two biggest ones. Do you mind if I just quickly answer Ken Fisher's question also, or perhaps
please.
he wants to ask it?
Ken, go ahead.
Well, Thomas, I was just interested, is this all pre-programmed? You talk about all these different deployments that need to be made, or is there somebody somewhere at the right time pushing the button? I'm just trying to understand. There's so many ways mistakes could be made. It suggests that somebody has pre-programmed all this. Help us understand that.
So when you land on Mars, somebody just talked about landing on Mars, everything has to be fully programmed. You say land, actually the last command you send to the spacecraft, roughly an hour or two before, is like, go land, and then you're done. You just sit there and everything either works or doesn't work, and you just wait, because light it's too long. It takes 20 minutes to go back and forth to Mars, depending on where Mars is relative to the Earth. It's not, okay, so this one was really different, Ken. So what we did is, so light only takes a few seconds to go there and back. So what we did is we commanded every one of these. It basically says, put the boom out. It does. It's like, is the boom out? Tell me, are all the sensors telling me that boom is out? Yes, yes, yes. Okay, good. Put the other boom out. So there's a team in there. Ken, my biggest pride is that they were working 2 shifts per day, deploying that telescope, and kind of really telling it. Half of the shifts, Ken, were run by my former student from Michigan.
Go blue.
Yeah, the guy sitting there, Robbie Swarsh, was the shift leader for half the shifts during this entire deployment, right? So it's so basically doing that. But yes, they were. So what they're doing is much more joysticking it. It's like kind of doing that, and there's a few things that needed to be programmed. For example, if something goes bad, the spacecraft needs to take over and save itself. Like, hey, if there's anything that you worry about, do this. So it constantly watches to make sure that nobody messes with itself in a way that, a bad command from the ground that would hurt it. So it's programmed, but it's a lot more joysticking than landing on Mars. It's a very different deployment characteristic.
Thank you.
I'm going to ask Brenda Amen to ask a leadership question. Thomas, Brenda, are you there?
I sure am. Thomas, thank you. This has been amazing. One of the things that sticks out, not about leadership, but about there being a planet for every star. I'm like, wow, I feel like such a speck in this whole universe. Yeah. So the leadership question is, what is it? I just hear the necessity of trust. I mean, mistakes are all around you. What is it that you can, what's your first go-to to create trust in a culture?
Look, I think you have to recognize that trust comes from consistent action. So basically what I'd spend a lot of time on is talk about the principles we're going to use. And then absolutely I'm consistent every time that we're focused on. And, you can't, as you know, turn on trust in an organization, right? You have to do that. What's really hard, and what I struggled with on this one, I needed to almost break the mission to make it successful. Because if you're wasting $600 million of taxpayers' money, you have to ask the question, can this team be successful? I actually had never any doubt that the engineers and the technicians could do this. I had doubts whether the leadership could do it, whether they put enough focus on it. Brenda, the most important predictor, I'm looking at all these missions. The most important predictor for whether a mission is successful is focus. Is the team focused on success and caring about success as much as I am? Are they wanting to be? Is in the team that again, that trust build, one of the mistakes they made is they put fasteners on that, that heat shield there. They put fasteners on and didn't lock them. So if you ever fixed a bicycle, you put a fastener on and you don't lock them, you know what happens? You drive down the street and after a mile or so, the fastener comes off. That's exactly what happened. It's an absolutely ridiculous mistake. Many people talk, oh, the stupid technicians. That's not what happened. I was not in the room, but the way this usually goes is somebody tells the technicians to do something stupid. And the technician says, is this really what you want me to do? It's something stupid. And the boss says, shut up and do. That's usually what happens, right? When you make a stupid mistake, that's usually what happens. So what really is part of this important trust building is to do that. So what I had to do is go after the mission. They were embarrassed in front of the whole nation with congressional hearings about it. So what I did is I never went in public against the company. Basically said, we're going to have to be successful together. I'm not going to throw them under the bus, even though many people said, oh, just blame them. They deserve all the, like, no, we also failed of not recognizing what was happening, right? And I have to tell you, I mean, I got this leader in place, African-American man who, grew up in a segregated school. I put this top leader in place, and he is both gentle and a bulldog. You know what I mean? He will not back off, but he listens to people, and I love this team into being, right? I mean, for me, he came from the top. He would defend them, but then he would give them a hard time, and we went from a schedule efficiency of like 55, 60% to 95% within a few months, so basically, if you do this, kind of trust can build relatively quickly, but again, consistent action does it.
That's amazing. Thank you.
We're going to have to wrap up for your schedule, Thomas. We could probably talk to you all week and just begin to tap the questions. I have one little question for you. It may be a huge question, but this week I'm with my wife. We're watching our 6-year-old and 8-year-old granddaughters in New York City. I'm coming to you from Queens this morning. What lessons from this mission, when I sit down tonight to talk to them, should I try to instill in them?
Well, look, I mean, for me, I look at a mission like this and I see what people can do when they come together. Like, I mean, for me, magnificent telescopes like this, finding a vaccine, whatever it is, kind of what I hope, the 2 lessons that your kid will understand is the night sky is incredibly beautiful. Look at it and appreciate it. And to understand the night sky requires that people come together and build machines that, frankly, are beyond the understanding of any one of us. But we can do it if many of us come together that are different from each other. We can do these things, and we can learn about nature in ways that make it even more amazing to us. That's how I talk to kids.
Well, thank you, Thomas. It's been fascinating to hear this. Thomas and I talked, I guess, 7 or 8 years ago about his next steps when he was at the University of Michigan Center for Entrepreneurship and School of Engineering, and this is the path he chose. We could talk a long time about some of the differences between being a professor and running this program. I'm sure there are many, many lessons. But again, I'd like to thank you from the deepest, I guess I usually say deeply from my heart, but I'll say from the deepest infrared messages we get from the universe. I thank you from there, Thomas.
Yeah, and thanks for the opportunity. Really appreciate it, bro.
We'll be back on June 3rd with another person who's talking about teams coming together, and that's John Bacon, who will be talking about his new book, which is about a hockey team in Ann Arbor. So thank you all for participating. We will post this on Monday, or actually probably later this week. No, let's say Monday. We'll post this video. So those of you that want, I know some of you said, I wish I had kept my kids home from school to watch this. Well, you could show them the video. And we will also post a way to reach Thomas if you have other questions or comments or any suggestions to him about how he could impart these lessons to other people in the world. So thank you so much, Thomas, and have a great day, great visit to Ann Arbor, and we'll talk to you soon.